morning or good afternoon or good evening, whatever it may be. GIS 201 here at Northern Virginia Community College. I just wanted to let you know I have some good news and some bad news. The good news, of course, is today is a snow day. The bad news is we move right along. Just like the world turns, so does the class schedule. Here is your lecture. I guess that's the bad news. Assignments are all the same. Rest assured we'll get everything squared away next week in class and go over what we need to make sure we're all on the same page and everyone understands the materials. But for now, I'm going to deliver your at least part of the lecture component that we would have covered in class remotely, so you can watch this and then do your teaching tutorials after you've read the chapter, and then do the assigned exercises in the syllabus. Otherwise, enjoy your day off, and I'll see you guys next week. So we're going to talk a little bit about Chapter 13, which is about geodatabases. And as always, ArcGIS has certain things about it as far as geodatabases, and this is sort of how the chapter is outlined, and we'll go over some of these items. So, Chapter 13, Geodatabases. What about them? Well, they're designed to store feature classes for a particular geographic area. It incorporates all feature classes, rasters, and tables in a single entity. In other words, it's a single storage structure that contains all the data types that you need, and it does so in a file system that has a spatial component. In other words, it defines a geographic area, and sometimes when you're carelessly adding things into geodatabases, you'll find out that if you're adding something that's from outside of the area that is defined as the geographic area of the geodatabase, it will not allow this to happen. Three types of geodatabases: personal, file, and an SDE. Personal geodatabases are based off of Microsoft Access, and so they're kind of required to have some of these kind of things. 2 gig size limit, and it's a Windows operating system only type setup. File geodatabases stored in folders. They're really good for single users or small groups, even large groups. You can have a lot of data, up to a terabyte. Works on multiple platforms, so they're pretty good setup. The SDE are the commercial geodatabases, things like Oracle and SQL Server, designed for multiple simultaneous users, and they support versioned editing. That's the big thing, versioned editing. It allows you to make changes, evaluate those changes, and if you don't like them, you can roll back to the previous version of the geodatabase. So what can go in a geodatabase? All feature classes, feature data sets, that's a collection of related feature classes, as well as tables, annotation, relationships, if you have formal persistent joins, for example, planar topology classes, and network topology classes. And this is just an illustration of what some of the things are, and how they can exist, and the different symbology that is there with them. So what are the functional applications? Geodatabases support a variety of data management functions to enhance work. Big things are like domains and subtypes, which allows you to control how you input data when you're filling out attributes and creating new elements, and essentially it makes for a more accurate, more topologically sound data set. Planar topology and spatial rules, network topology and connectivity. So if you're trying to control how things fit together or how networks function, you can do that with these databases. It also allows for relationship classes and version editing if you have an SDE geodatabase. So what are domains? Domains are rules about what can go in an attribute field. It's really just that simple. It reduces data entry and consistency errors. In other words, rather than typing in 1 inch, 3 inch, and 6 inch, you can simply put in 1, 3, and 6. Or perhaps you have a value that needs to go in that is a percentage, and it has to be between 0 and 100. This can prohibit you from putting in incorrect numbers. Subtypes would be, for example, you had a road network, and within the roads there were multiple types of roads. This would allow you to identify them by subtype and automatically display different symbols for each type. They might behave differently when you're editing. In other words, some may turn on or off at different degrees of zooming in and zooming out. Each subtype can have its own default values. You can put different resistances or different costs to travel on these, and which all of this can become very important for various network types of activities. Planar topology are the rules within and between layers. Things like must not have overlaps, must not have gaps, must not self-intersect. And so essentially, without planar topology, as the editor or the creator of the data, you're responsible for maintaining all this stuff. When you use a geodatabase and you have planar topology built into it, you can enforce these issues and go through and test to make sure that boundaries that should be the same are the same and such. Network topology, mentioned this briefly a little bit earlier. It's often used to analyze things like traffic and utilities. It's essentially the connectivity rules between a linear network. Things like 12-inch pipes can only connect to a 6-inch pipe if it goes through an adapter, that kind of stuff. It allows you to do things like finding paths or tracing areas that are up or downstream from a particular location in a network. Version editing, you can test what if, you can roll back to previous areas, you can resolve conflicts between multiple versions, it allows multiple people to edit geodatabases at the same time. But again, this is only with SDE geodatabases, and that's not what we're using. Schema. Schema is a full description of all feature classes, tables, fields, topology, and relationships in a database. Now, there's a couple of ways that we can have a schema. We can grow these through time in a database that's haphazardly assembled. It can be designed ahead of time for a specific ahead of time to fulfill specific organizational needs. In other words, you define your schema based on what you're going to need, what you're going to do, and then you build your database to accommodate that. It can be downloaded, shared, and customized. These are some examples of schemas, and essentially they're just diagrams of your database. When you look a little closer, you can see a lot more detailed information about what's going on there. Creating data sets. Designing good geodatabases begins with defining the purpose. So you need to talk to your users about what they need and what they're trying to accomplish with the data that they have, and what data that they have or anticipate having in the future. And you need to define the geographic characteristics like the area, extent, the scale, and the projection. And you want to list and organize feature classes and rasters so that they're easy to define. You want to define your schema, your fields, your domains, and your subtypes so that you know what you're putting in to your data. You want to plan metadata development, make sure that as you make changes to data that you update the metadata and record this. And you want to plan for long-term projects to develop a schema for creating and updating your data as well. So organizing feature classes, you keep similar features in the same feature class. They're easy to separate, difficult to merge. So some examples would be one feature class type with highway type field, and you can symbolize the field. You might be able to clip out just the highways or maybe just the other roads. They're easy enough to create geodatabases. You can do in our catalog. Simply select the folder where it's supposed to be, go down to new and click on file, geodatabase, or personal, or whatever particular type you want. You can also do it through Arc Toolbox. Once you have database created, you can simply bring the feature classes in. You can do it single or batch tools. You can use SQL to select substates. The coordinate system for the layers will be automatically projected if different from a feature class. So this is one of the good things. You can create the geodatabase in the projection that you want, and you can have other data in other coordinate systems, and when you bring them into the feature class, it automatically projects that data as needed. How do you make new ones? Well, you can simply go to the new feature classes, that is, simply go to the geodatabase and right click on it, go down, tell it you want to make a feature class, give it a name, and do what you need to do. You can then import or select the particular coordinate system that you need. You can put in tolerances. You can put in all the various fields that are going to be in the attribute table and all these things, and then ultimately hit finish. And you've created what you need. Now, you can also do feature datasets, which are related feature classes. They have a common coordinate system, and they may participate in topological relationships and networks, but they don't necessarily have to. Coordinate systems. Every feature class and a feature dataset must have the same coordinate system. This is important. Every feature class and a feature dataset. So you have this feature dataset like wildlife. In the wildlife dataset, you have feature classes like elk and bull moose and flying squirrel, and each of those have to be in the same coordinate system. The coordinate system is defined during the creation of the feature data set. If imported or created feature classes will automatically be projected into that coordinate system. So how do you create feature data sets? Again, very similar setup. Select them, pick your projections, talk about your tolerances, set all that stuff up, and then you're good. However, once a feature data set is created, the coordinate system cannot be changed. Using geodatabase features, we're going to look at domains, split and merge policies, and subtypes. Setting up domains. Domains are basically just rules for data entry. They prevent typing errors. You can verify that values fall into the correct range. You can create for an entire database. They can be reused in different feature classes, and so they're relatively useful. So what are some of the types? Well, coded domains is one. So for example, you have things that are difficult and annoying to type in, like 1/inch, 3/inch, and do you put a space between or not, and how do you do that? And you can end up in a situation where you might have three different types of, you might have 3 space dash inch, you might have 3 space dash space inch, you might have 3 dash space inch, you might have 3 dash inch, and so you could have 4 or 5 different ways you type that in, and it would keep them all separate, not understanding that it's really all the same thing. With a coded domain, you select those descriptions and then you give a code that corresponds to that. And so when you're entering the data, you don't have to type in 1-inch, you type in 1 or 3 or 6, and then it populates the other field with the preferred description that goes along with that code. And like we mentioned earlier, with range domains, you simply set parameters that says this answer must be between X and Y, and then it puts in the data. You put in the data, and it will only accept answers that are within the range that you specified. So what are the domain uses? Well, it saves space by storing numeric code, but set up domain for easy interpretation of values. And so the codes, for example, like 12, 14, and 16 may not mean anything if they relate to heavy industrial, commercial, or low density residential. And so in some of these instances, it's very, very important that not only do you have this mentioned in the metadata, but that you provide clear access to these sort of codes so that people can understand what it is they're actually looking at. So how do you add coded domains? You enter the domain name into an empty row, set the domain type field. You can set the split and merge policies, and then enter the code. You always enter the descriptions even if they're identical to the code. Users only see the description. So you want to add range. Again, similar setup. You just leave the coded values blank. It's very important to click apply after each domain is entered. If you entered several domains before clicking apply or OK, and one of the domains contains an error, it's difficult to figure out which domain has a problem, and you usually end up deleting everything and starting all over, and you don't want to do that. So assigning domains are assigned for one or more fields. They're assigned when the field is created or later. Domains must be assigned to fields of the same type. A short integer field can't use for a long integer domain. The float field can't be used for a domain name or double domain. So if it's short integer, it's got to stay short integer basically. If it's float, it has to stay float. Assign domains to fields. This can be done in our catalog. It highlights fields in the Properties tab. Highlight the fields in the Properties tab. Click on the domain box and then select one of the available domains. Only domains of the same type will be listed. If a domain is not there, check the field type in the domain and add the field. So how do domains work? They are most visible when editing coded domains. The field in the table contains a drop-down box instead of allowing the user to type the data. So instead of typing in what it is, you simply click a drop-down box and select the one you want. Range domains do not warn you automatically when you enter a wrong value. No impact until you perform a validation. When you run the validation, it identifies things that are outside the range, and then it flags them, which allows you to go back and edit those again. So again, how do we edit them? Well, coded domains show up in the drop-down boxes when editing in table or in the attribute editor. User selects the desired values. If you forgot to enter the description when you set up the domain, the values will appear blank on the form. Type in values normally. Ranges domains does not automatically warn you. Like I said, if it's wrong, it won't show up until you do the validation steps, and then it flags the ones that need more editing. Split and merge policies. When polygons are split into two pieces or merged together to make a single new polygon, the attributes must be updated. Depending on the type of attribute, different treatments are appropriate. Copy to the new one, leave it blank, partition or sum based on area. The split and merge policies control the behavior of the feature attributes when the feature is merged or split. This saves a lot of tedious work of re-entering all the attributes, and it prevents inappropriate assignment of data. Merge policies. Merge reduces data entry tasks when features are changed. Things like weighted averages, sums, and defaults. Crown cover percent is a new value based on area weighted average of the original polygons. So board feet timber, some of the original from polygons, and the ownership is default to the area. Merge policies are included in ArcGIS for consistency with other databases. However, they do not actually work in the editor. Instead, the user selects the features that define what the merged features attributes will be. Split procedure reduces data entry tasks when features are changed, i.e. duplicated, or using a geometry ratio or default. Cover type, no change. You copy the old values to the new ones. Example would be board feet of timber. It's allocated to polygons from a ratio of original polygons. Split policy. Let's look at subtypes. Subtypes are like different types of roads all within a road network. They're based on a short integer field. It's numeric code. A description is added for the display and interpretation, and that's kind of what the users see. So you can go in and automatically assign defaults as features, or you can add them during editing or digitizing. So what are some of the advantages of subtypes? Each subtype can have its own default values. Each subtype is treated as a separate layer during editing. If you have ArcGIS standard license, then each subtype can have its own set of validation rules. In other words, you can control the domains and the connectivity on each of the subtypes, and each subtype can have its own topology rules. Different default values can be specified for each subtype. This saves a lot of editing of attributes, although there may be expectations to the defaults. Old subdivisions have lead sewer laterals that can be edited if they're needed. Overall, editing is reduced. Each of the attribute fields may in turn have domains, so you can nest options and choices within options and choices to ultimately make it so that your data entry becomes more about selecting within specified ranges or selecting from drop-down menus as opposed to entering each piece of information individually every time, and thus providing multiple opportunities for increased numbers of errors. During editing, each subtype is treated as a separate layer. When a feature is added, it automatically takes on the default value of its subtype, and so if you don't make any other notions, it's going to stay as what it was. When to use subtypes: when the feature class has a limited number of clearly delineated types, then subtypes work really well. When setting different defaults for each type, subtypes are very useful. When the topological or network behavior of each type is different, that's when you should use subtypes. So how do you do this? The first step is you got to plan for the subtypes. Establish the following properties for each of the feature classes. What subtypes will be used? Are they complete? What are the attributes of the feature class? Domains that will be used. Split merge policies for each attribute. Default values for each subtype as applicable. So here are some examples. Subtypes for a waterline feature class. You have a water main, a water lateral, a sewer main, and a sewer lateral. Attributes and domains for the water lines. So the various attributes for the feature class can be pipe diameter, pipe material, install date, maximum flow. The domain for the geodatabase could be the diameter could be coded, the materials could be coded, and the flow could be a range, because you know that in your particular system everything's somewhere between 0 and 2,000 gallons per minute. To create the domains, open the geodatabase properties, create the domains, and remember to click apply after each one. It's kind of your classic save. You save like you vote in Southern West Virginia, early and often. The idea is, what you want to do is apply after each one, and that way if something doesn't work, you know it was that one that didn't work and not one of the last 12. Creating new feature classes, there's a feature class tool in the data management toolbox. You can also that you can use to do this. You can add the subtype field. It's a short integer field. It contains the codes. It creates it in the field tables of the layers properties in our catalog, and also add it to the other fields. Click on the subtype tab. You can choose the line type that you're interested in, enter a code, and describe each of the subtypes. So let's look at some defaults for these various subtypes. Different default values can be specified for each subtype. Saves a lot of time, like we mentioned. You can set the defaults for each one and what they're supposed to be. And once you get to that certain point, you can stop all this and start doing the editing. Know that each subtype has its own template. Choose the desired feature and then add it. After the features are added, they take on the default attributes of the subtype. And look at all the work you saved. Editing annotation. Do you remember what annotation is? In Chapter 3 we learned to create annotation and save it in the map document. Now we're going to create and edit it in a geodatabase. First thing is you create dynamic labels. Use the symbols property to set up the initial annotation properties that you're looking for. Then from the table of contents you convert your labels into annotation, and you store it in the geodatabase, and you do all the other things. Make sure you store it the right one, etc., etc. And you get your initial results. You can then use your editing tool to select the annotation and begin to move things around and edit them as you need. So click on the roads annotation template, choose the construction tool, type text in the annotation construction box, place the annotation using the method appropriate to the construction tool. So one of the ones we're looking at here is to move text, and so the annotation box has various handles, and so that allows you to shrink and enlarge and to move or rotate around things so that they better fit. You can also look at the attributes table, which is the attributes for the annotation. There you can set the font size of symbols and select the annotation that appears in the window. There's different ways to create your annotation. For horizontal, you can click on the map once and place it. For straight, you can click once to enter the anchor point and again to establish the angle of rotation. You can use leader line annotation. Click on the place, the far end is the pointer, and then click to define the near end and the place. You can follow feature annotation, and then it will, as you see in the example here to the right, it will literally follow along the contour of what it is that you're putting it with. You can use curved, enter a start, middle, and end point, and you can control how that annotation is positioned. You can make existing annotation follow features. It's pretty straightforward. The way you do it, you select it, you right click to follow the feature, click on the center of the annotation and drag it around until it fits the way you want following the feature. You can stack annotation for a better fit. So you have a really long label and you don't like it that way, you can click on it, you can stack it, and it allows you to go from one long label to a stacked label. So some more editing. There are other techniques for editing annotation. Essentially, this just gets you started. You need to look at the help section in ArcGIS if you're interested in additional ways you can modify these things. This concludes the Chapter 13 lecture. There's a lot of information. You need to read the chapter. Take your time. Read it very carefully. Geodatabases are wonderful tools. They prevent a lot of errors and they can really help you become better at GIS. But you have to understand what they can and cannot do and understand how they can and cannot cause problems. So listen to what I've said in the previous slides, read the chapter, do the teaching tutorials, and then do the exercises as assigned in the syllabus, and you should be well on your way to understanding geodatabases. Thanks for listening and enjoy the rest of your snow day. Goodbye.